Hello, everybody. Welcome to our latest IREM seminar. This one is actually going to be a little more traditional. We're going to hear about some really cool research that's actually being done on campus at Georgia Tech. And so our speaker today is Harish Ravichandar. He's currently a research scientist in the interactive computing here at Georgia Tech, working with Sonia Chernova. And his background, he did his bachelor's in control engineering at Anna University in India, then a master's at the University of Florida, PhD at the University of Connecticut, and he's then moved to do a postdoc here at Georgia Tech, and now he's a research scientist. He studies mainly human-robot teaming, and that's what I think his talk is going to be about today. And he's won some pretty cool awards, both in teaching and in research, which is a really impressive combination. In fact, he was recently awarded the Outstanding Research Scientist Award here at Georgia Tech. So he has a pretty solid background both in the instructional side as well as the research. He's involved in a pretty cool Army program. That's how I got to interact with him. And today he's going to tell you about human-robot teaming. I think he's got a pretty interesting title. It's called From Coexistence to Collaboration. And before I hop into the talk, I just wanted to remind you that we also have a seminar next week. So we have a little bit of an off-cycle schedule this year because of the COVID situation. So tune in next week for another exciting talk. But let's focus on this exciting one we have before us. So take it away, Harish.
All right, thank you so much, Ari, for the kind introduction. Let me share my screen. Thank you so much. I'm Harish Ravichandar. So today I'm going to be talking about moving from coexistence to collaboration, or towards reliable collaborative robots. So primarily, this talk is going to talk about building collaborative robots that can learn to reliably operate in unstructured environments while leveraging and enhancing their interactions with humans, right? So this is a lot of words. I will try to break this down and move on to the discussion. So I thought we will begin with the question of why, right? And I was thinking about how to motivate this talk, and I thought some historic or perhaps prehistoric context might be relevant here, right? We're all familiar with this picture of evolution, how we transformed into being Homo sapiens from being primates. Perhaps a less popular depiction of this process is the following, right? There's a lot of cool research in anthropology in the recent decades, especially, that talks about the role of collaboration in our evolution and how it was predominant, one of the predominant features that enable us to be at the top of the food chain like we are being right now. In fact, we also got pretty good at collaborating with other species. This is actually an art from a book called The Invaders. It describes a pretty cool story of how Homo sapiens learned to work with wolves in order to be able to defeat Neanderthals and be able to survive. So the talk I'm going to give today is focused on how we can develop such truly collaborative relationships with robots, right? Moving away from traditional notions of where robots just coexist. All we want from the robot is to not damage the human. How to move from there to have robots that can truly collaborate with themselves and with us as well. So, of course, we need to answer this question of who really cares about it, right? Perhaps this audience is very familiar with the very many applications where this will be useful, right? We could think about manufacturing environments where the robot can play a significant role in being able to collaborate with humans and perform these tasks that are not easily automatable, right? How we have done so far. We can have robots that can collaborate with humans so that they can do a part of the task that humans are not so good at, and humans can do the tasks that the robots are not so good. And of course, there is a huge investment in this here, and I want to draw your attention to the highlighted numbers on the right. It just shows the growth rate. You can see how many collaborative robots are projected to be used and bought as compared to the numbers above, which talks about traditional industrial robots. And of course, there is autonomous driving. Even if we are able to completely realize autonomous driving, the possibility is that they will have to collaborate with other autonomous cars and cars that are driven by humans, in addition to pedestrians and people on bikes, for example. And there's a lot of money, of course, being invested in this area for autonomous vehicles. And there are defense applications where it makes sense for having robots that can collaborate with humans in order to accomplish a variety of tasks, try to make it more safe for the human beings, and also have more efficient systems. And The next one would be the role of assistive robots or personal robots, where robots can really help elderly people and people with disabilities to be able to live a more independent life, right? And this is actually an interesting diagram that shows the population distribution in the world as time progresses, right? As you can notice, a large fraction of the population is starting to occupy more elderly ages, and as this is continued to grow, and it is expected to grow even further as we go, we really need technology that can answer society's questions, such as being able to support the elderly. And of course, there are many notions of how we will be able to think about these robots. And as I mentioned, there are people with disabilities who might benefit from having an assistive robot that can perform their tasks and make them live a more independent life. And there are so many statistics in how common disability is and how many disabilities can use something like an assistive robot, for that matter. So what do we really want from robots in terms of being able to be useful in all these domains? I argue that we want three things from robots, right? One is reliability, the other one is awareness, and the other one is coordination. And together, we can have robots that can truly collaborate. So how do we really get there? What I'm going to talk about today is taking a three-pronged approach, right? Or three different sets of tools that will help us get here. One is learning. The other one is estimation, where you're able to estimate with the learned models. And the other one is structure. You will see an underlying approach across all the different techniques that I'm going to discuss today is the fact that they all have a certain sense of structure in them, so that you don't have to learn models from scratch. You're not trying to infer things from scratch. There's going to be some structure, and this structure either comes from physics or either comes from domain knowledge. So first, let's talk a little bit about the reliability side of things. So the question here that I'm going to first discuss is how to reliably learn these skills from humans, right? How can we learn these skills? And the answer I'm going to argue is by exploiting structured learning from demonstrations. So here, in this particular context, what we really want is robots that can work in unstructured environments and still have reliable performance and be able to adapt to sudden and unexpected changes, right? To be able to really work in kitchens that look like this, right? I promise this is certainly not a picture of my kitchen, but just to say the point that we really want robots that can work in these sorts of environments. And here is an example, right? On the left, you have a robot being taught how to pour water in the cup, right? So this was actually demonstrated to the robot, and then now it knows how to pour water into the cup, right? So, but we are really interested in scenarios where the cup might be in a different location. There can be unexpected disturbances that can come up, right? What we want the robot to be able to do is adapt to these changes. Here in this video, I'm actually moving the cup, and the robot is still able to complete the task. So there is a lot of related work in this space when it comes to learning from demonstration. You can think about learning directly policies from demonstration. You can think about optimization techniques like inverse reinforcement learning, where the idea is to learn the underlying cost function that's being optimized. And when you think about just learning policies, you can think about learning either dynamical systems as state-dependent policies, or you can also think about learning the probabilistic distribution or the geometric methods that come with learning from learning movement primitives. And within learning from dynamical systems, you can think of learning stabilizing functions, where you have a dynamical system that you learn from the data, but it's not inherently stable. So you would have to learn some forcing functions that stabilize those systems, or you can inherently design stable dynamical systems that are guaranteed to be stable. And we will talk a little bit about this. And even within that, there are techniques that either use Lyapunov-based methods or contraction-based methods. In a little bit, I will give a more context with respect to what these methods mean. Just to situate the related work, these are the categories in which the work I'm going to talk about falls under. Of course, there are numerous trade-offs in these decisions, right? And this is a perfect time for me to give you a shameless plug of one of our recent survey papers in the area of LFT, and where we discuss several categorizations and the different trade-offs involved in choosing between these categories. So I'm going to talk about one of my approaches called contracting dynamical systems primitives. So in this particular approach, there are three distinct contributions. One is that this is a method that can learn dynamics of goal-directed motions, right? Motions that have a goal. And we want to learn these from demonstrations using contraction analysis. And the second contribution is that we can guarantee convergence of the robot's end effector, irrespective of what the initial conditions are. And the third one is that we will be able to see how this enables instantaneous adaptation, sort of like how we saw if the cup is moved all of a sudden as the robot is moving, it should be able to instantaneously adapt it. So here's a block diagram overview of this process, right? So you start with demonstrations. You can provide demonstrations both in the position space, also in the orientation space, so you can learn force dynamics. So you will take this data and you're going to learn these dynamics under some constraints, which will become clear in a second. And we're going to use these trained models in order to be able to generate trajectories to the robot so that it can reproduce it in scenarios and be able to have a reliable performance as an output. So let's talk a little bit about how these dynamics are encoded, right? We are going to think about statistical dynamical systems that can be used to encode these dynamics. So we primarily want to learn time invariant dynamics because we want it to be state dependent so that it can be robust to changes. Here, the idea is we want to learn the dynamics of these state variables. And we are going to learn that by approximating and learning the joint density of both the state and the state derivative using a Gaussian mixture model. And of course, Gaussian mixture model will have a bunch of parameters such as the means and the covariances of each of your Gaussians. And the idea here is to use a rigorous over the learned model. In essence, what you will be computing is a closed form expression for the conditional expectation of the state derivative, which will give you an idea of, given a particular state, what should be the state derivative, which means for the robot, it means given a particular state, how it should move from there, right? Of course, you have a closed form expression which sort of has a nice structure. If you take a close look at it, it looks like a convex combination of linear systems, but of course, the weighting factor is the nonlinear element in it. So what is this contraction analysis that I talked about, right? So contraction analysis is nothing but differential analysis. It primarily asks the question of how do solutions of dynamical systems evolve with respect to each other, right? So assume you have two trajectories as here in red. They are nothing but two different solutions of the dynamical system, just that they started slightly different initial conditions. And as time evolves, they evolve. The trajectory gets formed. And let's assume we can think about virtual displacement between them, right? Sort of a distance between these 2 points. And now you can imagine asking the question of how does this displacement evolve in time? And that's precisely the question contraction analysis asks. And it turns out if a system is contracting, these trajectories will converge to each other, meaning the virtual displacement will diminish as time evolves. So are we done here? Can we just learn systems that are contracting? Not quite. There's a little bit of a nuance here, right? Consider the diagram on the left. What that shows is a set of trajectories, let's say, that you want the robot to be able to recreate, right? And you want to learn the dynamics. If you notice the plot in the middle, what it's showing is the Euclidean squared distance to the target point. You can see that it's not monotonic, right? If you do traditional contraction analysis, you will conclude that the system is not contracting in the Euclidean space. Because, of course, it goes away from the target first and then goes into the target and reaches and converges into the target, all the trajectories. So this means that just taking a Euclidean sense of distance really limits the kinds of systems you can learn under this paradigm. So what we want to do is have a sense of generalized square distance. Actually, turns out if you find the appropriate metric that defines this distance, that is the plot you're seeing on the right, you can see that that distance is actually monotonically decreasing. And you can analyze the system using this generalized square distance to prove contraction. So we are going to look at what's called generalized contraction analysis, where the distance measure is now given by what's called a contraction metric that defines a non-Euclidean version of the distance. And we are going to think about the rate of change of this distance, right? If you actually compute the rate of change of this distance, you will get an equation that's in the middle. What I want you to focus on is the fact that there are these highlighted elements that are dependent on the dynamics itself. Meaning, if you're approximating the dynamics with a Gaussian mixture regression model, those parameters of those statistical models will appear here in this equation. So what we want here out of this equation is that we want to make sure that this rate of change is strictly negative. All that means is that it will converge and go to zero and the change will be monotonic. We can ensure that the system is contracting. So we can derive the closed form constraint that if enforced, you can make sure the statistical dynamical system is contracting. So in order to learn this, we cast this as a constrained optimization problem. What you have here is nothing but set of parameters for the Gaussian mixture model and the set of parameters for the metric that you want to learn. This is because you might not necessarily know what should be that metric, what should be the definition of a distance. So the idea is to be able to learn it directly from demonstration. And the equations you saw in the previous slide are nothing but, the cost is nothing but the reconstruction error, and the constraints are the ones that were derived using contraction analysis. And the additional constraint you see are making sure the robot will reach to a specific point, as well as making sure you are learning a valid statistical model, such as probabilities have to add up to 1. So there is a theorem that we were able to prove that says that if we are able to learn a Gaussian mixture model under these specific constraints, it ensures that the resultant dynamical system is contracting, right? And what does this really imply? This implies that the robot motion is guaranteed to converge to the goal location. But there is a slight issue here, right? So the issue is as follows. If you look under the hood, these constraints have this for all x at the end. What that really means is this is a set of infinite constraints for a continuous state space. And of course, that's not computationally tractable for us to implement. So we came up with a solution that focuses on sum of squares decomposition so that you can turn these state-dependent constraints into constraints that are not state-dependent. Of course, they tend to be a little more strict, but what it lets you do is it lets you turn these infinite set of constraints into a finite set of constraints that is more computationally tractable, and you're able to learn the system. So, of course, many of you might be wondering, all of that is great, but does this actually work, right? So what you're seeing here is a qualitative representation of how the model is able to learn a variety of dynamics, right? So this is a popular data set used in the field, that there are several goal-directed motions that we are going to learn. And you can see that it fairly accurately is able to reproduce many of the trajectories from the data set. So it means that it's able to capture a wide array of dynamics. And note that for all these different dynamics, it's the same approach that is learning these dynamics. Right? And even more specifically, if you notice that the plots in the middle, you can see that you can learn different local dynamics depending on where the state space is. This is the advantage of casting this as a problem of time invariant dynamics, meaning depending on which local region of the state space you're in, you will be able to learn different kinds of dynamics. And that can become very helpful. Right? In terms of numbers, in terms of quantitative results, we were able to compare this approach with a variety of state-of-the-art techniques, and we were able to see that when it comes to accurately reproducing demonstrations, what you see on the left is the particular metric we use that computes the error or the reconstruction error or the reproduction error between what the robot is able to do versus what was demonstrated. And we were able to see that we were able to do consistently better than prior work. And there are two versions of the approach that I have listed here. The primary difference is the class of metrics that define the non-Euclidean distance, right? Without going into much detail, it just represents two different versions, one with a more complicated notion of distance than the other. And of course, the more complicated your notion of distance, the better you will be able to do in terms of capturing complex dynamics. Okay, so the reason why I'm flipping through some of the slides, I apologize, is because I'm not able to get rid of the slides I meant to hide in the presentation mode, so bear with me. So the other thing is also being able to learn orientation dynamics, right? So in addition to position dynamics, like I talked about, you can also learn orientation dynamics. And when it comes to orientation dynamic, we again try to compare the approach with some of the state-of-the-art approaches that were able to learn these orientation dynamics. And we measure the performance in terms of this reproduction error, except of course now you're in the quaternion space. So there is a log quaternion error for measuring the difference between what the robot did versus what the demonstration was. And we were again able to do consistently well compared to the baseline. A key point to note here is this approach also ensures that the trajectories for orientation that you generate are guaranteed to stay within the quaternion space, right? So it's not that you're going to rely on post hoc normalizations. You can make sure you can learn the statistical dynamical systems in the acceleration space or the angular velocity and acceleration space. and then directly make sure you're using closed form expressions for the quaternions so that you're guaranteed to stay in the quaternion space. So we also did a couple of tests where we had tasks and that looked at reliability specifically, what it means in addition to being able to see those trajectories, what it looks like on the robot. Here you're seeing that the robot is doing a sorting task, but then I keep annoying the robot by not letting it complete the task. But as the robot is trying to do, I keep perturbing the robot's motion, but it consistently comes back and tries to complete the task because it has a time invariant dynamics model for how it should move from different parts of the state space. On the right-hand side, you're seeing the same video you saw earlier. As it's trying to pour the water, I switch the cup. It realizes now the goal location is different, right? So you can simply achieve this by translating the entire dynamical system, and it can instantaneously adapt and understand that the point is to pour the water into the cup as opposed to a predetermined spot. So next, we can turn to the question of what characteristics of a skill are important, right? So we looked at how to learn these reliable skills, but of course we made the implicit assumption that we know in what space, in what kind of characteristics we need to capture about the skills. But it might be true that in many cases you are not sure what sort of skills you need the robot to capture or what characteristics it needs to pay attention to. So our approach to solving this problem is, what if we learn simultaneously different characteristics and also learn how to balance these characteristics? So that's what led to this approach we call multi-coordinate cost balancing. So in this particular approach, imagine there are these two demonstrations, right? So this is just a toy example with two different demonstrations as shown here. And now, if you insist that you want your system to just recreate the Cartesian, in Cartesian coordinate, you want the robot to recreate these reproductions. What it will try to do is it will try to just average them out, right? This would lead to very non-smooth trajectories such as this. And of course, one could argue you can add a smoothing regularizer to this, but even then, it will try to just do the average, which might not be the point of these demonstrations, right? You can also think of other differential coordinates in which you can learn the same motion. You can define tangential coordinates, right? Where you try to reproduce the demonstrations in the tangential coordinate. And if you try to reproduce them, this is how they look like, right? So they roughly approximate a numerical velocity, right? Or the speed of the robot's motion, but still it doesn't quite accurately capture all aspects of the demonstration. Similarly, you can go one step further. You can think of Laplace coordinates, right? Where you are thinking more about the curvature of the trajectories now. And while here the reproductions in green show that you are able to get a smooth trajectory because it's able to mimic the curvature of the demonstrations, but then it misses the point about the particular location, right? So what we propose is a balanced set of learned systems that capture the dynamics in or capture the distribution of trajectories in all these different coordinate systems and be able to combine them so that you can effectively reproduce, right? So here is a block diagram approach of how we are going about this. So you will have demonstrations, presumably in the Cartesian space, and then you can apply these coordinate transformations. And what you do is you simultaneously learn the density in each of these coordinate systems with respect to time, right? So you know at any given time where you should be with respect to these three different coordinate systems. And of course, you can define a reproduction cost in each of these coordinate systems. And what we do is we define the cost such that it's weighted by variance, which means that you don't really want to penalize the robot for deviating from the demonstrations when the demonstrations themselves are widely different, right? What that says is there's something about the covariance, or there is something about the precision actually, which is the inverse of the covariance, that tells you how important certain regions of the demonstrations are. So we weight the cost based on that. And in addition to that, we also learn a set of weighting factors that will tell you the relative influence of these different costs. And we do this by directly learning these weights from the demonstrations. And ultimately, if you combine all of these costs together, and this cost balancing can go offline, and when it comes to execution time, you can simply solve a convex optimization problem. And you can also make sure you solve some constraints, such as you want the robot to go to a particular point, or you want the robot to go through a waypoint. All of those constraints can be taken into account, and you will be able to do trajectory optimization. Right, so we tested this on different tasks. What you see here is a qualitative summary of that. All the orange ticks that you see here specify what was the most influential coordinate system for that task, right? We have 4 tasks here. We have handwriting, picking, pressing, and pushing. You can see that different coordinate systems played an important role when it comes to different tasks. What you see in green, however, is the best performance, right? So you have these baselines where only single coordinates were taken into account. And we also tested it on another baseline where we asked the question of, is it really important to learn these weights from demonstrations? Can one not just simultaneously learn in all coordinate frames and uniformly weight all coordinate frames? Turns out it works very well for handwriting tasks, but it doesn't quite do so well when it comes to picking, pressing, and pushing. And we are able to see that the approach that we present, where we adaptively learn the relative influence of these different coordinate frames, performs well across all the tasks. All right, so let's switch gears a little bit. So we talked about how we can reliably learn skills for robots and how they can execute it with guarantees, right? Let's talk a little bit about this concept of awareness, or getting to know something about the partner that the robot has, about the human, right? In the interest of time, I'm going to provide small teasers of how we think about this space, right? So we are asking this question of how can we learn and anticipate human behavior? And the answer is that we can infer and predict behavior based on learned models. We just looked at how we can learn from demonstrations of humans, right? So one way to think about these demonstrations is that the humans are teaching the robot how to do tasks. Another way to think about that is these demonstrations are also indicative of how they do tasks, right? If you have a particular human and a particular set of demonstrations, it says something about how that particular human does tasks. And we can exploit that. We can learn those models and use those very models as predictive models. And that's what these works do, right? So here is an example where we have a maximum likelihood approach that tries to predict which goal the human will reach. It can work with multiple humans in parallel. What you're seeing is a couple of my colleagues back in Connecticut are trying to reach for different objects placed on the table. It's able to accurately and quickly infer which object that they are trying to reach, right? So this is done because we have predictive models. This is because we know how they reach, and there is a model that captures how they reach, the dynamics of their capture, and you can design a maximum likelihood approach that will be able to predict where they reach. Of course, we can also test it on other data sets from other publicly available data sets. This one is a particular one from Cornell, where there are several reaching tasks that people do, and we're able to use these models. And another additional feature of this particular version is that it also updates its model as it sees the human move, right? Which means that it's not just it's relying on whatever data set it was used to train, it also adapts its model as the human is moving. So presumably as time goes, it will get better and better at working with a particular human. So after this, we asked this question of, could we do something about having a prior distribution, right? So turns out the previous method does not scale very well when you have a lot of objects in the scene with a lot of clutter, right? So the next set of next intuition that we exploit here is that it turns out people look at the object that they're trying to reach, right? Seems obvious, but how can we capture this information as a prior distribution and do Bayesian filtering on this? And that's precisely what this approach does. So what this approach does is it computes a prior distribution, so you can sort of narrow it down to which set of objects are likely to be reached by the human. So you can compute a prior distribution, and you can use multi-hypothesis filtering to figure out which particular object that the human is going to reach. What this lets us do is we are now able to operate in very cluttered environments, right? I think if I remember correctly, there were about 24 objects in the scene, and the algorithm was able to do really well here. Okay. So next, let's move on to the part of coordination, right? So we talked about how robots can learn from humans to reliably operate. We learned about how robots can make predictions and understand the humans that they are operating with. We can also think of a scenario where the robots need to coordinate with themselves or with fellow human beings as they operate. So here, we are going to first ask this question of how do we leverage diversity? When it comes to diversity, what I mean by diversity here is consider a team of robots, right? Or a human-robot team, where you have several humans and several robots, each of them having their own set of capabilities. There are different types of robots, right? The question we are interested in is, how can we exploit this diversity to be able to solve really complicated tasks? So the answer that I propose here is trait-based task assignment, which means that we are going to look at what are the characteristics of each of these agents within this team and effectively exploit their relative advantages and disadvantages. So as an aside, multi-robot task assignment as a field, of course, is pretty popular. There is a huge set of approaches in the literature that tries to attempt this problem. And here's one popular way to categorize these approaches, right? So they can be categorized along 3 dimensions. One dimension is the task type, which means whether you need a single robot to achieve this task or whether you need the collaboration of multiple robots. And the other one is the robot type, which means can these robots simultaneously do multiple tasks, or do they have to focus on one task at a time? And then there's also this notion of allocation type, which talks about whether you want to instantaneously assign tasks to the robots right now, or you want to think about scheduling problems where you want to worry about what will come next, right? So the discussion today will be limited to single task robots and multi-robot tasks and instantaneous assignment. So let's talk a little bit about this algorithm we have been calling Strata. And this is the heterogeneous team I was describing, right? An illustration of one. You're seeing different types of robots here, different types of even humans here. And let's say they all have different characteristics. What you see as colored bar graphs here, nothing but distributions of their capabilities or traits. And we are calling this species trait distribution. And we also can think about tasks having requirements and constraints, right? So there are, let's say, 4 tasks here, and each of these tasks have their own requirements of what it is that you need in order to successfully achieve this task. And these constraints can also be incorporated. Imagine if these tasks were to happen in different physical locations. And it is that in this particular case, there is no way for a robot or a human to move between tasks 2 and 4, or the locations of tasks 2 and 4. You can model that using this task graph, and we call this the task trait distribution. So when it comes to the task assignment problem, we are primarily interested in finding how to distribute and assign these robots along this task graph when you're given certain task requirements. If you're told these are the requirements for a task, how would you effectively make sure robots end up in particular tasks and form what are called coalitions that make sense and that are required to achieve the desired requirements, right? What I want to stress here is we do not assume that we know what would be the desired distribution of the agents. In other words, we are not simply interested in just moving the robots on the task graph. We are interested in figuring out where should robots go in the first place? How should they collaborate with each other? How should the humans and robots form teams so that they can achieve different tasks? And we do this by computing optimal transition rates. What that means is maybe they're all distributed in at different locations at the beginning, irrespective of what the task requirements are. And once you know the task requirements, we are going to look at how to move them around the task graph such that they will end up in particular places that make sense so that the task's requirements can be achieved. So as a block diagram, this is what it looks like, right? On the one hand, you have the species trait distribution, meaning your capabilities of your team. On the other hand, you have these desired task trait distributions, which means that you have a set of task requirements for each task within your mission. Now, both of these sets of information is being given to the algorithm that we call Strata. What it does is tries to figure out the transition rates on the graphs that results in effective task assignment. That, as you can see, there are different coalitions that end up forming for different tasks that are suitable for that particular task. So here are the core contributions of this work, right? We proposed a unified framework to model capabilities in the first place, right? Unless you model what the capabilities of the agents are, you will not be able to think about how they contribute to task success. We also model these capabilities in both continuous and stochastic way, right? Especially in comparison, prior work had looked at binary instantiations of these traits, meaning they were simply looking at whether or not a particular trait existed in a particular agent. We are interested in seeing, can we develop continuous and stochastic models? Can we make fine differences and reason about the differences? For example, if the payload of a certain robot is 5 pounds and another robot's payload is 15 pounds, we want to be able to differentiate. And we also have an algorithm that does task assignment with respect to 2 different goals. One we call exact matching, which means whatever the requirements are, you need to meet it perfectly. And the other one we're calling minimum matching, which essentially means that you are not going to be penalized for over provisioning. You just have to meet a certain certain bar. If you go above it, that's fine, is the objective of the second kind. So here is how the traits are modeled, right? So each team we assume is made up of a finite number of what we call species, which are nothing but groups or types of agents. And each species is defined by its capabilities, right? Within the species, of course, there might be a little bit of variation, but we assume that they all belong to a family or a species, and that's how we are going to model traits. As you can see in the diagram, you're seeing that is let's say there is an example particular team which has two traits, right? The trait 1 and trait 2, and what you're seeing is the distribution of different species. This is what we call the species trait model that tries to figure out and model the capability of each species. So one thing to note here is once you're able to capture this model this way, it becomes very scalable with the number of agents you have, right? Once you're able to cluster the agents into this mix, it doesn't matter how many agents belong to each species, because the way we formulate it, it just becomes a numerical value on a matrix and does not increase the dimensions of the matrix. In other words, it doesn't increase the dimension of the problem. And we have this potential to model both human and robots here. Especially when you have human teammates, you're likely to have a lot of variation even within a particular species, right? And this particular way of modeling takes care of both the differences between species and within species. And we also make note of the fact that some traits are cumulative and some traits are non-cumulative. What we mean by that is you cannot have two slow agents and make up for a faster agent, right? But if you have different payloads, they could add up, they could aggregate. So we take specific care about differentiating between cumulative and non-cumulative traits. And we also model agent distribution as follows. So assume that the robots are distributed across the task graph, and the distribution of agents is denoted by X here. So, and you can think of the dynamics of this distribution given by this equation of a dynamical system. What this basically looks at is at what rate agents are entering and exiting the task, right? So this will help you model the physical movement of the agents on this task graph. And you can look at these set of rates that we call transition rates that dictate how fast you want the movement to be. And we can also set limits on how fast each agent or each type of agent can possibly transition. So the overall modeling framework, after all these particular modeling choices being made, turns out you can represent this as a linear system of equations where you have on the left-hand side the task trait distribution. On the right-hand side, you have the agent distribution or the task species distribution and the species trait distributions, which means that the multiplication of the two matrices that represent where the robots are and what are the capabilities of the robots inherently gives you in this model how different capabilities are distributed across the task. And we solve this optimization where we say, okay, so here is the desired set of requirements that I have, and here is the team that you have available. How will you distribute the agents? So we implicitly identify how to distribute these agents by computing directly the transition rates on them. And as I mentioned earlier, we can have two different goal functions. We can say either these requirements have to be exactly met or they just need to be satisfied. And of course, what we want out of this optimization is that we want the agents to converge fast, and we want stability, which means that once they converge, they stay there. And we also want minimum variation. Notice that the traits are stochastic here, right? Which means that you're only going to get a distribution of traits on these tasks, and you want them to be minimally varied, because otherwise you will not be sure whether the particular set of agents that you had in that instance will satisfy the requirements. So we explicitly minimize the variance in the optimization. So we evaluated this in numerical simulation where we had 8 tasks. We had 5 species with 200 agents within each species, and we considered a total of 5 traits, 3 of which were cumulative. And we had a total of 100 independent randomized runs, and we compared it with a baseline model, which assumes that traits can be modeled as binary factors, which means that this model only considers the existence of a trait, meaning can this robot carry things as opposed to the specific payload. And we measure the performance in terms of 4 different metrics, and they can be classified as follows. The metrics on the left compute exact matching error, which means that it just looks at the distance between what was achieved versus what was needed. On the right, it looks at minimum matching, which means that it only looks at how much under did you fall, which means if the requirement was 100 and you reached 105, that metric will return an error of 0. But if you fell at 95, it will give you 5, right? And on the top, you have metrics where the actual distribution of the robot's capabilities are deterministic, meaning there is not a lot of variation within those species. And the other metric here is a different condition where we measured what would happen if the distributions of the capabilities are randomly generated, right? Which is much more similar to what would happen if you have a lot of humans in it. In essence, what we see here are these 4 different metrics when you are optimizing for exact match, right? So let's just talk about what these graphs mean. On the top, what you're seeing is that this approach is able to consistently do better when it comes to satisfying trait requirements, both in terms of meeting it and as well as making sure you don't overshoot too much when it comes to deterministic scenario. And it does this consistently from the beginning, right? These graphs are illustrations of what happens as time evolves. At the bottom, you're seeing what happens when these characteristics are randomly sampled from a distribution. We find that here, too, the approach is able to do better than the baseline, and it does better on average. Of course, on average, because there are outliers where that doesn't quite hold. But consistently, on average, it does perform better. So this is what happens when you do exact matching, when you try to meet the requirements perfectly. So now let's take a look at what happens when you try to do minimum matching. Means you just are trying to meet the requirements, right? So the graphs look slightly different here. A better way to make sense of them is to think about them as the graphs on the left and the graphs on the right. So the graphs on the left, the key takeaway here is that this approach is a little more efficient than the baseline. What that means is it doesn't over-provision as much. Whenever there is a certain requirement, it makes sure it doesn't provide too much more than necessary, which means that it's efficient at utilizing the resources. That's why you see that for the baseline, there is a very high variance and the average is much higher in terms of exact matching. On the right-hand side, you're seeing that similar to the previous set of results, we are able to consistently meet the requirement better than the baseline. An important factor here is all the results from the previous couple of slides were computed based on the runs that converged. But here is a look at how many runs actually converged out of the 100. Here is where is the key takeaway. When you do not consider the nuances of a continuous trait space and the stochasticity of it, it turns out that just simply considering the binary existence or non-existence of traits results in situations where you simply cannot solve problems because it is not nuanced enough to meet the requirements of the problem. So it ends up such that the optimization is never able to find solutions. On the other hand, if you're able to carefully consider those options, you're able to consistently meet the requirements better. We also tested this on a game of capture the flag, a similar to game of capture the flag, where we wanted to see this trait satisfaction or this ability to meet requirements, does it translate to team level performance? It turns out, so we define a set of tasks, they have different requirements, and we had 3 different teams. It's that one team follows the proposed approach, and the other team follows the baseline approach, and the other team, for the sake of sanity, we also tested what happens if you just randomly assign tasks. Right, you do no reasoning. Clearly, you can see that whenever you are playing against random, both the baseline approach and the proposed approach do consistently better than random assignment, which just means that even reasoning about the mere existence or non-existence of traits is much better than not reasoning at all, right? As a sanity check, that makes sense. And we also compared the proposed approach against the baseline. And we can see that we are able to consistently result in winning teams, formation of winning teams, which means that again, the careful consideration of these traits and how to distribute agents across tasks is much more beneficial compared to the baseline. So what's next, right? We looked at these 3 different pillars of how to realize reliable collaborative robots, right? We looked at reliability, we looked at being able to understand humans and make predictions about them, and we looked at how they can collaborate, right, with themselves and with humans. So there are several questions that are left unanswered here. In terms of reliability, it's not yet clear how much structure we need, right? It's not clear how much structure you want to impose into the model versus learn from scratch. It's not clear how exactly we can scale to high-dimensional problems, especially if you have the capacity to capture demonstrations in multimodal context. And there is also this question of, can these approaches be extended to contact-rich manipulation tasks, as opposed to simply just going for goal-directed motion? In terms of awareness, we can ask questions related to how to treat humans as more than mere obstacles. I showed a couple of examples of how we can make predictions of how humans move, but we still need methods that can effectively take those predictions into account in order to have adaptive robot behavior that does not merely consider human as just an obstacle to avoid. And in terms of coordination, there are these questions of, can we learn to coordinate, right? So one of the things that was difficult with the methods presented was this specification of task requirements. We assume that some magic oracle will provide these requirements, but of course it's challenging to provide these requirements. The question I'm interested in here is, can we learn these task requirements directly from data? And there is this notion of risk-averse task assignment, right? So the stochasticity of the agent capabilities and in fact, the stochasticity of the tasks themselves, can this be modeled in a risk-aware framework where you can guarantee and say things like, this is the minimum, maximum amount of risk I'm willing to take. What is the best possible assignment we can come up with? I think there is a full rounded theory that can be developed there. And we can also think about learning task requirements directly from data in addition to high-level coordination. So I would be remiss if I do not acknowledge all my collaborators, mentors, and students who contributed significantly to some of the results that you saw here. And in summary, I want to conclude by saying that I argue that there are these three different capabilities that the robots must possess in order for them to be able to effectively collaborate with us as opposed to merely coexist. Thank you for your time.
Okay, thank you, Harish. Sorry for some of the technical issues. It looked like actually things had been working and I was the problem, but that works too.
Oh, okay, all right.
So if there's any questions, can people post them in the Q&A or in the chat? Either one is fine. Then Harish can answer them. I can relate them to him too. Can you go into more detail about the connection between contraction analysis and learning a Gaussian mixture model? I'm guessing you mean by GMM.
Sure, absolutely. So what we are specifically interested in is the following, right? So the problem is of learning statistical dynamics from demonstrations. And Gaussian mixture model has been used for a very long time now, I think probably for more than a decade, in being able to capture these statistical dynamical systems. But oftentimes, these are statistical dynamical systems, which mean when you regress over them and we are having robots operate along these dynamics, you don't have any guarantees. They will have spurious attractors. They will be attracted to spurious equilibrium points. Sometimes there will be instability in the model, which means the robots can move in really erratic ways, right? What we are interested in is developing a set of constraints so that these dynamics are guaranteed to be stable, right? Of course, there is some prior work that has looked at how to do this using Lyapunov method. And it turns out, of course, finding the Lyapunov candidate is difficult. And of course, it's not a necessary and sufficient condition. It's only just a sufficient condition. Contraction analysis gives you this nice framework of convergence. And it tells you specifically, this is the necessary and sufficient condition for the system to be contracting. So that's what we exploit, right? So this work computes the specific constraints you need to impose on the parameters of the Gaussian mixture model so that the learned model is guaranteed to be stable, which is what, as a side benefit, is what you get as robustness, right? So when the robot is moving, if it is perturbed, it knows how to move from that point in the state space. From any point in the state space, it knows how to converge to the specific goal location.
Cool, thank you. I don't see any other questions, so I'm going to ask one. I thought the stuff where it was inferring which box it was going to place something in, or the person was going to place something in, was pretty cool. Can you explain to me how that algorithm works sort of at a high level again?
Sure, absolutely. Right. So the idea there is you have these learned models from human demonstrations, right? So let's say the human showed you how they move 5 times. You've now developed a statistical dynamical system that will capture this movement. What this does is it exploits state estimation techniques in order to predict what will happen in the future. And you can do this 2 ways, right? There is one approach that took a maximum likelihood approach. In that approach, what specifically happens is this goal location is now a parameter of this dynamical. That's what guides this dynamical system to make the movements. And what you want to do is come up with an estimation algorithm. In this case, it was an expectation maximization algorithm we designed that will specifically identify which parameter makes the most sense. So it's a maximum likelihood estimate. The other one is just a Bayesian version of it, where we found a way to fuse prior information that you get from gaze, and you can run, again, Bayesian inference on it to predict which goal location makes sense to.
So essentially, you were leveraging the dynamic model that you'd already learned.
Exactly.
To try and predict where it would go in the future.
Exactly. Yeah.
Cool. All right. So a question from Sam Deal. Is it a bigger priority to try and replace humans in routine roles or try help aid humans do their job better? For example, many people are not satisfied with talking to an answering machine, but many people use a recorder to remember things.
Okay. I'm trying to make sure I understand the question. Is it a big priority to try to replace humans in routine tasks or helping humans do their job better? I think that's a very interesting question, right? And also a nuanced one. I think the idea would be to, of course, replace, try to automate menial tasks that humans don't want to do. That's an obvious answer. That's what we've been trying to do for a long time now, right? In addition to that, there is, of course, something to be said about how robots can play a collaborative role in order to make sure they help humans do their task as opposed to be a nuisance. So many of the stuff that I'm working on directly translates to scenarios in which there is a need for human to be present, right? So it's not that the robot can single-handedly or autonomously complete all these tasks, but it specifically looks at scenarios and tasks in which there is a need for the human to participate. And when there is a human in the vicinity of the robot, it's about how the robots can operate in a way that it helps the humans, right? And be able to truly collaborate, as opposed to just merely exist and do its own tasks.
Cool. Any other questions? Give it a couple seconds. Okay, it doesn't look like it. So I think we should all thank Harish. Oh, one more, sorry. Do you see the question as well, Harish?
Yeah, I'm reading it right now.
Okay, so I'll read it out just for the audience. Sure. How does the idea of time invariant analysis and weighting coordinate frames translate to dealing with sounds? How would we learn the dynamics of recreating voices?
Interesting. I'm not sure if I'm qualified to answer that. I will simply state that if there is a way to generate voices, that all you need to do for that is to capture some underlying dynamics. And of course, the dynamics now depends on different characteristics, meaning the curvature of how the trajectories will change, or the different geometrical aspects or topological aspects of those trajectories. Then yes, you certainly can use a meta approach like this to capture different characteristics and effectively combine them to generate them. But that's as far as my knowledge goes when it comes to generating voices.
That's good. All right, so it looks like that's it. So I want to take the opportunity again to thank you, Harish, for giving a great seminar.
Thank you.
I hope that the audience did as well. And so let's all thank him for a great job. And just a reminder, next week we'll have another seminar. This one will be on applying for faculty positions. So it'll be a group seminar with a bunch of the end faculty from around IRIM. So we look forward to seeing you then.
All right. Thank you, everyone.